Hello friends, welcome back to my YouTube channel. In the previous video, we have seen that Griffith theory is applicable to brittle materials only. But what about the materials that deform plastically? If the stress at the tip exceed the yield stress, then the material near the crack tip start deforming plastically, and this is called plastic deformation zone. Orowan came up with the addition to the Griffith theory so that the equation can be used for materials that deform plastically. He included the plastic work in the Griffith's equation gamma p. So the Griffith equation was 2e gamma s by pi a to the power half. Orowan added the gamma p, that is plastic work, in the Griffith's equation. Here gamma s is the surface energy, A is the half crack length, and E is the Young's modulus of the specimen. Later, Irwin proposed that gamma p is difficult to measure, hence we can replace 2 gamma s plus gamma p with G. G is the strain energy release rate, GC, that is critical strain energy release rate. So GC is critical strain energy release rate. So we can write GC as dou U naught by dou A. Here the rate refers to, it is not with respect to time, it is with respect to crack length. So that is the reason we can write GC as strain energy release per unit increase in crack length. Now if we want to see the modified equation, that will be Eg by pi a to the power half. This is the modified equation. Now how to determine G? How to determine GC? The critical strain energy release rate. For this, let's assume we have a material with a crack length of A1. The other material has a crack length of A2. Now because the crack length of the second material is larger than the first object, then the crack extension force or the force required to extend the crack in the second case will be lower. So if this is the plot of force versus the crack extension, the force required to extend the A1 crack will be higher compared to force required to extend the A2 crack. Let's say the slope is F equal to m delta. M is stiffness here. It's like spring constant F equal to kx. So the slope of first equation is m1 and the slope of second curve is m2. The area under the curve, that is elastic strain energy, it will be half F delta, and we know F equal to m delta. We will replace delta here, it will become F square by 2m. Now the second case we assume is we restrict the displacement of the material. Now let's say if A1 is the crack length in this material, the second crack has a length of A2 and the displacement in the material is fixed. Delta 1 will be equal to delta 2. So in that case, when we apply the force, the curve looks, this will be A1 and this will be A2. The displacement will be same, F versus delta. Here delta 1 will be equal to delta 2. Because delta 1 is equal to delta 2, this is the slope of first curve and this is the slope of second curve. We know F1 by M1 will be equal to F2 by M2. This shows that F by M is a constant. It will remain same. Now we partially differentiate this equation. 1 by M dou F by dou A plus F dou A 1 by M equal to 0. This will give dou F by dou A equal to minus Fm dou 1 by M by dou A. And now we know strain energy release rate G is equal to dou U naught by dou A. That will be equal to dou by dou A. We know U naught is equal to F square by 2m. So G will be equal to, we will take half outside, dou by dou A F square by m, and that will be equal to 1 by m 2f dou F by dou A plus F square dou by dou A 1 by m this will be 1 by 2 1 by m 2f. We know dou F by dou A is equal to minus Fm dou 1 by m dou A plus F square dou 1 by m dou A. Here m will be cancelled and this will become minus F square dou 1 by m dou A. So G will be minus half F square dou 1 by m dou A. Now if we plot the curve of inverse of stiffness with crack length, then the curve looks like this, and here this is critical crack length. The slope is dou 1 by m by dou A. Now at a critical length, so below this critical crack length, the crack propagate in a stable manner. However, above the critical crack length, the crack is unstable. It propagates catastrophically. Hope you like the video.